Welcome to homework.
So in this case, we're asked to look at a case where we have a block and spring that's suspended from a ceiling here that's then oscillating. And we're told to measure y from the static equilibrium of the system. So that means that in this case, where we measure y is 0, this spring is stretched, and it's stretched by an amount of whatever the weight of this block was. So what we can think about is that the unstretched length of the middle of the block was here when the spring was unstretched, and then we have some static deflection there, and then we're going to measure our motion from that point here. So if we draw a free body diagram of this block, we have mg acting, and we have the force in the spring, and the force in the spring is the change of length. So the change of length is whatever y is here, plus the static deflection. So that's the change in length. That's the motion of this part, of this end of the spring. The motion of this end is this, so we need to take the difference of those two. So we get this minus this, and that's the change in length of the spring, the total change in length from when it was unstretched. Plugging that, we get my double dot minus equals mg minus fs, which is then this. Okay? And what we can see here is that the static deflection is actually mg over k. So k times the static deflection is mg. So that's just all these two terms is basically a static force balance. So if we had statics, let me actually write that better. K delta static, that would be this equation of static equilibrium for this system, where this is just the static displacement from when the spring was unstretched. So y now measures the motion about that static equilibrium, and that's usually what we worry about in vibrations, because in vibrations, constant forces don't cause systems to vibrate, they just cause the equilibrium position to change. And so usually we're just worried about the motions about an equilibrium. So these terms cancel and we get this. And we can either write it this way also, but we can take this and we can basically just write down the solution from what we've had before in previous problems. So we have the homogeneous solution that has a frequency of the natural frequency, two constants that we find from initial conditions. And then we have the particular solution, where in this case f naught equals k delta, so f naught over k is just delta naught, and then we have 1 over the frequency ratio in the denominator times sine of omega t. Okay, whatever this term was here goes into here. So if this was a cosine, this would just change to a cosine. And so this is our final solution, and we have again our forcing frequency is part of the solution is part of this motion is oscillating with the forcing frequency, and part is oscillating with the natural frequency. And those things will constructively and destructively interfere with each other again and again, and it will look actually like a very complicated motion, but it's really only two frequencies combined.